Good morning. I'm Yan. Thank you for listening to my talk. I'll be talking about Chiron, high concurrent throughput communication for IoT devices. This is a joint work with my colleagues, Suzanne Xinyo, and my advisor, Dr. Ting Zhu. And again, we're from the University of Maryland, Baltimore County. What motivates our work is this statistics from Cisco, which shows that nearly the projected traffic use for the internet. So this is the projected traffic use. It's on the x-axis, which shows the year. And you're talking about exabytes per month, which is on the y-axis. And the majority of internet traffic is going to be video. So it's going to be video on demand or internet videos. That's compared relatively minor to the gaming and file sharing and other web sources. This again is the same statistics from Cisco, which shows the number of exabytes per month. And what this figure demonstrates is what we all know intuitively, that videos are going to be coming to wireless devices, your laptops, your mobile cell phones, your wireless TV. Very few devices in the future are going to be connected via the wire. So you're not going to watch Netflix on a wired computer, right? Ethernet computer. So this idea that Wi-Fi traffic is going to carry most of your high throughput, high bandwidth demanding, low latency video traffic is what's driving this critical issue with IoTs and heterogeneous radios. So IoTs is going to increase exponentially also. They're estimating 20 billion within a couple of years. And to demonstrate this problem, we're going to use Zigbee. Zigbee is a very common, as described before, Zigbee is a very common low energy radio. It controls everything from smart lights to motion sensors to temperature control. And in our example here, we have another Wi-Fi that's going to be streaming some sort of video, right? So currently, this was described by the previous group. Currently what happens is when a Wi-Fi gateway needs to talk to a Zigbee device, it sends its information. And due to CSMA and other factors, the Wi-Fi stops transmitting momentarily. So when the Wi-Fi gateway wants to continue that wireless traffic, the Zigbee packet stops, and then it sends in series to the Wi-Fi device. And in the reverse, this is also true, right? So the Zigbee device needs to send a packet to the Wi-Fi to the gateway. The Wi-Fi pauses its communication, and then the Wi-Fi transmits when Zigbee is done. So in other words, the IoT radios must transmit in series. So what happens if Zigbee and Wi-Fi do not sense each other? So the hidden terminal issue where you can't sense one another, or there's some sort of accident with the CSMA, you have a packet collision. If you ever run Wireshark, you'll see this every once in a while with your Wi-Fi data. And when a packet collision happens, the packet is completely dropped. It shows as a corrupt packet, and the acknowledgement to that the packet was received does not happen. And then Zigbee and Wi-Fi devices know there's a packet collision. I need to do a retransmission, right? So to illustrate this problem in further detail, this is a simplified example. So we're talking about 802.11g, 20 megahertz. In 802.11g, and when we compare the channels of Wi-Fi and Zigbee, there are 4 channels of Zigbee that overlaps the Wi-Fi channel. So in Wi-Fi channels, we talk about this idea of subcarriers. Each subcarrier is like a stream, so it's like a showerhead, right? It streams out multiple concurrent, simultaneous groups of Wi-Fi data. Not all the streams or not all the subcarriers are overlapped. Only a certain portion of it is overlapped. There are 7 subcarriers of Wi-Fi that overlaps one Zigbee channel. So therefore, only a few subcarriers are affected, but that causes the entire packet to be dropped. To further illustrate this issue, this is a spectrum analyzer which is monitoring your Wi-Fi traffic. So the y-axis is time, the x-axis is the frequency, right? So this is the shared frequency between Wi-Fi and Zigbee. So again, the narrowband 2 megahertz package signals you're looking here, these are Zigbee packets. They're transmitting data. As discussed before, the wideband packet is the Wi-Fi. And as illustrated, the Wi-Fi and Zigbee cannot transmit simultaneously. They're in series. So when Zigbee transmits, the Wi-Fi temporarily pauses. And when the Wi-Fi transmits, the Zigbee temporarily pauses. So the result of this is this major issue. There is a huge opportunity cost. There's tons of spectrum that's wasted between this communication between narrowband and wideband signal. So also to illustrate the problem more severely, so when there's a huge difference in spectrum efficiency. So spectrum efficiency is defined as the number of bits that are sent per second per hertz. So how much information is used during time and frequency, right? So Zigbee is extremely low compared to Wi-Fi. So when your entire network switches over to Zigbee, you lose a lot of throughput compared to Wi-Fi when Wi-Fi transmits. So all this is as motivates our idea that we must have very efficient wireless communications for the future. So we ask the question, is there a better way to do this, right? Is there a better way that which we can transmit Wi-Fi and Zigbee signals together? And the answer is yes. So we make this observation if you look up the physical layer of Wi-Fi and Zigbee. The physical layer of Wi-Fi uses sine waves to transmit your bits, right? It maps bits to sine waves. And Wi-Fi uses a very, very slow sine wave. It operates in kill symbols per second, while the Zigbee chips is at 2 megabits megachips per second. So there's a huge difference between kilohertz versus megahertz. So we want to seek to see if we can relax some of the assumption. The assumption is that you must have a perfect sine wave. Wi-Fi must use a perfect sine wave to transmit each symbol. We want to say that, is there a way that we can make it such that we may not have to form this perfect sine wave and embed Zigbee data inside the Wi-Fi packets? And remember, there are seven Wi-Fi subcarriers. There's 7 Wi-Fi sine waves which we can use to produce this Zigbee signal. So in essence, our experiment demonstrates that, or tries to demonstrate that we want to embed Zigbee data in Wi-Fi packets, and vice versa. During reception, we want to see if we can separate the Zigbee signals from the collided packets from the Wi-Fi packet and recover information from both. So to illustrate this, that is our design goal. So to change it, we want to be able to concurrently send a Zigbee packet and Wi-Fi packet simultaneously, such that both devices can demodulate this information. So how do we do this? So I'll talk briefly about how does a Wi-Fi and a Zigbee radio work quickly, and how we change some of the designs. So Zigbee uses what's called spread spectrum. Spectrum is basically, for every bit, you multiply by a 32-bit pseudo-random number. The pseudo-random code is shared between the transmitter and receiver. So you're spreading out each bit to a larger bandwidth. This gets sent to an OPQSK modulator. The modulator is just something that maps the symbols or the bit sequence to a specific sine wave. And in Zigbee, there are just four phase states. So it maps bits to these 4 phase states, right? Wi-Fi operates on a slightly different principle. Again, the analogy to Wi-Fi is a shower head with multiple streams of water that's coming out simultaneously. So what happens is you have this block of bits. This block of bits is chunked into little bits together, and then it's going to transmit these little chunks out simultaneously. So it does what's called serial to parallel chunking of the bits. That's the chunks of bits, which we call symbols, are then passed to the modulator to a quad modulator. Now, the modulator, again, just maps it to sine wave, but the difference between Wi-Fi and Zigbee is that Wi-Fi uses both phase and amplitude modulation. So there's phase states and there's amplitude states in this modulator. And well, normally that just gets sent to an IFFT, which just maps each groups of sine waves to its own frequency, right? But however, in the way that we changed it is that for the overlap subcarriers, for 7 overlap subcarriers, we create a signal combiner, which just basically takes those seven Wi-Fi subcarriers that are overlapped and modify a little bit such that it could contain also the Zigbee data in there. That gets sent to the IFFT, the inverse Fourier transform, which allocates each subcarrier to its intended frequency such that it can be transmitted simultaneously. We append a standard training sequence to it. The training sequence is nothing but for Wi-Fi devices to synchronize its timing and phase information such that it knows how to compute the phase, and for signal discovery also. This gets sent to a Wi-Fi front end. The Wi-Fi front end just takes that signal and shove it to, transform it to 2.4 gigahertz, which is our example where it transmits that information. That gets irradiated by an antenna. Now, we want to also do the reverse. We want to take a collided Zigbee and Wi-Fi signal and then be able to recover both signals, such that we can concurrently receive data from both. So how does this work? Well, we have a Wi-Fi radio and a Zigbee radio. Again, they send sine waves. The sine waves gets changed to an electromagnetic wave. The wave goes on to antenna. The antenna produces a voltage. The RF front end digitizes those signals and then transform it back to what we call the baseband, or where you operate on the sine waves, so you can figure out the phase of that sine wave. So initially, it looks for a training sequence. The training sequence, again, is the Wi-Fi's way of saying, hey, I'm here. Here's where my sine wave begins, so you can begin to compute the phase states. This goes to the reverse of the inverse Fourier transform, which is the regular Fourier transforms, which just puts the subcarriers into its own channel, such that you can, or its own frequency, so you can begin to do the reverse mapping of the sine wave phase states to its the symbols and bits. So, and we add a signal separator for the overlapped Zigbee and Wi-Fi subcarriers. There's an equalization process that happens. So in normal Wi-Fi, this equalizer exists because when there's human movement, when you're in a room and multipathing that happens, it removes some of that the Doppler effects and a lot of the echoes in the room. It basically removes noise. In this instance, we also add a couple filters, passband filters in there, just to smooth out the signals further, especially on the overlapped subcarriers. So the equalization happens, the denoising happens. We do the inverse mapping from sine waves, phase states to the symbols, and out comes the Wi-Fi bits. Now, from the signal separator, we also know the portion of the signal that's overlapped. We apply an OPQSK demodulator, which just, again, does the inverse mapping. We multiply that, each groups of 30-bit sequences, by the shared pseudo-random code, and out comes the Zigbee data bits. So from this design, we were able to recover both the Wi-Fi bits and Zigbee bits when the signal collision happens. So I'm going to talk a little bit about evaluation. I guess I'm running late on time, but so we did line of sight in a hallway, through a wall, non-line sights. We did some human movement, mobility movement, and we just all had a wearable Zigbee where someone took the Zigbee and put it in its pocket or wrist and just walked around with it. The idea is we have one Wi-Fi channel. We added multiple Zigbees and computed using a spectrum analyzer of what happened. The vector signal analyzer allowed us to compute the spectrum utilization by measuring the frequency that's used. So the y-axis, it's bits per second per hertz, how much information is sent with the resource used, and the x-axis is number of Zigbee devices. So our baseline is a dual Wi-Fi Zigbee radio. When our results show that using this concurrent communication, we're able to improve spectral utilization by 16% fold. We also did throughput measurements, which is shown on the y-axis. This is Wi-Fi, so it's megabits per second. We did multiple scenarios, line of sight, non-line of sight. And the traditional Wi-Fi radios fall back to a slower modulation due to interference, such that, and because of that, the throughput was limited dramatically. Our Chiron gateway outperformed the traditional Wi-Fi almost every instance. Just a little bit more results. We did multiple Wi-Fi devices, multiple Zigbee devices, which shown the x-axis and the throughputs. And in every instance, our concurrent communication, as expected, outperformed the traditional gateway, traditional router. So finally, I also want to show the impact of traditional Wi-Fi radio. So with a just Wi-Fi radio with no Zigbee, we have this dark bar chart. And when we add Zigbee devices, the throughput drops dramatically, again, because of interference and because slower modulation states. But however, our Chiron gateway almost approached as though if there was no Zigbee present within our Wi-Fi network. So amount of time. In conclusion, what happens is we made a Chiron which is able to use concurrent transmissions between Wi-Fi and Zigbee devices. We leverage this idea that Wi-Fi and Zigbee has dramatically different symbol and chip rates, and we were able to filter and use that, leverage that. So therefore, we were able to design a Wi-Fi and Zigbee signal combiner and a separator during concurrent communication, and we show that the spectrum utilization is much better compared to the traditional Zigbee and Wi-Fi dual radio gateway. I'll take any questions. That concludes my talk.